Hey guys, it's Sierra again. Last time I saw that the video cut out right as we were getting up to the simulations, and so I'm here again today. We're going to do a brief recap about the EM, and then we're going to get to the most important part, which is simulating the data and looking at the EM algorithm as it goes. But first, big class announcement, you guys. You're supposed to have a midterm Thursday, but Dr. Lehman's going to push that back. And you guys are going to have a midterm next Friday, April 17th. From what I've talked to him about, this exam is going to be a very introspective exam. It's going to be able to show you whether you're understanding the material or not and really assess your ability. So, I've known Dr. Lehman for a while, and this is what this means. He wants you to keep studying, and for any topic, not only EM but other topics, he wants you to really go in and understand the mechanics of it. So I know we've been talking about estimators, so can you understand when to use estimators? Can you decide which one's better? What are the pros, the cons? Really going into depth about the material. For those that are taking the QE, this is definitely not a time to take a step back and relax. It's almost the time to keep pressing on. While the date was pushed back, keep working hard. Dr. Lehman's also, again, I've taken a lot of his classes and I know him pretty well. He's not too worried about distinguishing A's and B's, but he is very, very big about distinguishing from the A and C. So here's my advice. Work hard on the material, really put a lot of effort in, make sure you're writing down and explaining to him in all these projects and homeworks that you understand the material, you can understand the differences, and make it look professional. Put in the effort and you will get the grade you want, okay? So for this homework, for EM homework, for your written homework, for the midterm, put in the effort, make sure you're understanding all the details. So for us to understand EM, let's get back to it. The last couple of classes, we've seen this algorithm written out. What I did this time was I wrote out the theory as well as what we're going to implement today in our algorithm. So let's just start from the top. With your EM, you're always going to have to initialize your parameters. So in this case, you're going to have to initialize mu0 and sigma squared 0. I'll talk about that when we get to the sims and how I did it. Then, for a certain number of iterations, we're going to iterate over t. Another way, where t is some large number. Another way we can do this is through convergence criteria. So another way is in a while loop where you're looking for the theta difference, which is equal to theta of t minus theta of t minus 1 is less than some tolerance. So there's two ways you can do it. You can iterate over some large number, or you can do it through a convergence criteria through a while loop. I will show you guys what I did, which was the while loop. Now the first step is taking the expectation of the log likelihood. Okay? Let's just take a quick look and remind ourselves what that log likelihood was. It is going to be the product over the observations, but right here we have pi, which are the weights. We have this indicator function, and then this is the density. I just didn't want to write it all out. This indicator function right here is probably the thing that most of us forgot when we wrote this out the first time. But we need this here because it's important when we start taking the expectation, and it's that light switch that's telling us what part of the what cluster component our observations are in. Now, after some algebra, you guys can see that we can also rewrite our likelihood as this. The reason we want to convert it to something like this is so that when we take the log likelihood, we simply just have this blue part coming down, and it's easier to work with mathematically. So the next thing with this E step is taking the expectation with respect to our latent variable, which in this case is C. And so really that expectation, if we were looking at the log likelihood, is just going to come straight through and focus solely on this guy, that indicator function. And what it's saying, the expectation of the indicator function is just the probability of that event happening given all of our other stuff. Let me write that down. It's so the expectation, of our indicator function is simply the probability we observe that community assignment in that cluster given our mu k's and our sigma k's and our data. Okay? So expectation of indicator function is just the probability. Now we use Bayes' theorem to derive this. Go back to the last lecture if you don't remember all those steps. And then for notational point, we call it WIK. Now, these can be seen as weights. I know in the machine learning world and Chris Bishop, they call these responsibility weights. More different terms, it's all good. And don't care how you look at it, you're using Bayes' theorem to get there. Okay? Once we figure out this step, the E step, and this W, we then have our Q function, which is this blue part, and then this green part transforms into our WIKs, because we just solved for that. Then all you're going to do is argmax, take a derivative, i.e. take a derivative set equal to 0 with respect to your parameters, and you're going to get these two formulas, mu and sigma squared. Okay? On your homework, you're going to be doing the same thing of deriving this step, but in the p-dimensional case. Again, let me remind you, you're going to be working with vectors and matrices, so don't forget to go to your derivative cookbook and refresh yourself as you go through it. You can also see this as a weighted average. Now, this is all fine and dandy, but let's look at some of these sims and look at how it works. So in our sim, don't know if I can make that brighter. I'm going to generate some data of 500 points. We're going to have, our first case is going to look at dimension 1 with 2 clusters. The probability vector is just the probability, so that's our pi k's. We're going to have 0.4 and 0.6, and then we're going to have our mean at 0 and 3. So let's just generate some of that data and see what it looks like. Boom. And so here we have one cluster at 3 and one at 0. The sigma, or the variance, is 1. Okay, so now what we want to look at, get rid of that, is for my simulation, I did the convergence. So I'm saying that our algorithm will stop once mu t minus 1 is smaller than this tolerance. This type random I'll talk about in 1 second, but all this is going to do is just run the EM algorithm. It's busy, and what you can see from here, let me just show you. This right here is my initial start. So I started at 1.4 and 1.7. Algorithm just looped through it a lot of times until my difference was smaller than my tolerance. Now let's look at our mu estimates. Our estimates that we got from the EM are 0, pretty close to 0 and 3. So in my book, I would consider that successful. We also have our sigma estimates, which are pretty close to 1. If I want to get this a little closer, I could just increase my, actually decrease my tolerance, not increase it. And then let's look at our pi estimates. We have, ooh, 50-50. That's interesting. I'm curious on, but does that make sense to our data? It kind of does, because if we relook at our data, there's a lot of overlapping. There's a lot of overlapping right here. So there's going to be some issues. So let's see what happens to our algorithm when we pull those apart a little more. So let's make this 10. We're going to create some data. We're going to run this. So this is our data that we generated. And we're going to look at our estimates. This is where we initialized. So 5 and 6 pretty close to each other. And then our estimates are 10 and 0. Awesome. Those are pretty close. Our sigmas are pretty close to 1 in my book. And then our pi's, 6 and 0.4, which match more. So this is something you guys are going to also have to investigate and in your homework for small number data, for sample size that's small, and for higher number of clusters, and even higher dimension. Okay? Now, let's just run this one more time and see something interesting, hopefully, if it does. Ah, perfect. So same data set, but what's different right here is now we have 0 and now we have 9. And so what's happening is our computer can't really tell if we're calling our orange cluster orange and our blue cluster blue. So there's that label identifiability problem. And so what we really want to make sure when we're doing this is if we look at our mu estimates and our pi estimates, is that those two are lining up. Okay, so here's our truth. We had a mu of 0 corresponding to 0.4 of probability. Mu 0, 0.4, 10, and 0.6, close enough. And so you want to make sure those are matching, but it's going to be pretty hard unless you encode it somehow to make it very specific. Okay? So let's also just kind of continue this one more time through a different type of data. So we're going to have 3 components. 1, 2, 3. And we're going to look at our estimates. So we have 0, 5, and 8 as our means. And we have 7.9, 0, and 4.9. Those are close in my book. The variances are still 1. Those are pretty close. And then the pi's are also pretty close to what the truth was. So we have 2.6 and 2. We have 2, 0.2, 0.2, and 0.56. Pretty close in my book. So let me just show you a rough idea of the algorithm that I have. So I have a lot of if statements, but here I'm going to initialize. And there's 2 ways that I've initialized, and that's the type. I can randomly assign, uniform randomly assign labels, and then take the mean and variance of that to start. Or if you have higher dimensioned or harder problems, you can do k-means and use that as an initial starting point to start. This is very common for problems to use one algorithm for another algorithm. So I put forth to you guys that you should try that as well. But here's my algorithm. Here's my while. We're keeping count of the iterations, but I'm going to do the E step, and then I'm going to do the M step. The E step is just figuring out the probabilities that each point would lie in each cluster. The M step is then just computing the average, mean, and variance. So it is pretty simple. I'm not going to show you my actual code for those steps because that is your homework, and I encourage you to get started as soon as possible. So one more time, we'll go to higher dimensions just to show you guys it works. And so if we had higher dimensions, we have cluster 1, 2, and 3. We will see that that. There's my means, and my estimated means are right here. So again, we have the label switching issue, but do we have one that's 4 and 5? 4 and 5. Do we have one that's 5 and 0? Right here. And then we have one that's pretty close to 0 and 1 and 0. And so high dimensions, this also works. For your homework, again, reiterating, there's 3 things that you really want to make sure you do so that you can show Dr. Lehman you're putting in effort and understanding the material. That is, first, when does the algorithm work well? And showing that. So that's really showing when those 2, 3, 4 clusters are really separated. That shows that your EM algorithm works. The second is, start looking into the limitations of the algorithm. So start looking at maybe when clusters are overlapping, or higher dimension, or sample size. So those are the questions. And then 3, making sure you write about it, and especially in high dimension. Make it look professional. That's all I have for you guys. I hope you've enjoyed learning about EM. Last note, anything with coding and your midterm, start early, start now. Don't get off the gas pedal, because this is the time you're gonna shine above everyone else if you keep working hard. That's it, you guys. Have a great day.